Okay.
Hello, everybody. Today we have the pleasure to have as a speaker Professor Lotfi Ben Romdhane from ISITCOM, Sousse, Tunisia. Professor Ben Romdhane is a professor in computer science with a major specialization in artificial intelligence and social networks analysis. He is currently affiliated with the University of Sousse, Tunisia. He is a co-founder of and is actually leading the modeling of automated reasoning systems research lab specializing in the design and analysis of complex systems. His research activities span the general area of intelligent systems and are focusing actually on social networks analysis, influence, maximization, information diffusion, and community detection in social graphs. His works has been published in well-known specialized international journals and conferences. Professor Lotfi has obtained his PhD degree from the University of Sherbrooke in Canada with excellent honors and have been added to the honor list of the University of Sherbrooke for excellence in research. He has been awarded the CIDA doctoral fellowship. He is currently member of the Senate of the European Mediterranean University. The talk of Professor Ben Romdhane today has as title Mathematics in Artificial Intelligence, Contributions and Challenges. Please, thank you again, Professor Ben Romdhane, for accepting our invitation, and please, you can start.
Thank you very much. First of all, I would like to welcome the audience and hope they will enjoy my talk today entitled Maths in Artificial Intelligence, Contributions and Challenges. I would like to thank the Department of Mathematics, College of Science, Imam Abdul Rahman bin Faisal University for this webinar, for this invitation. Special thanks are due to Professor Rafiq Hagesh for his personal invitation. And let's first move to some information about me. I'm actually professor in computer science at the Institute of Computer Science and Telecom, University of Sousse. Actually heading a lab, MARS, Modeling of Automated Reasoning Systems, which is a research lab specialized in complex, let me say, systems. I'm holding PhD degree from University of Sherbrooke, Canada, with excellent honors, and engineering degree from ANSI, Tunisia, both in computer science. My research area is in the general area, let me say, of artificial intelligence and is centered mainly around complex social network analysis, reasoning systems, and distributed computing. Let's move to the summary of our talk. In the first part, I will introduce some main concepts of AI in order to get used to what is AI, how it works, and so on. Then in the second part, we will move to a deep learning, which is a kind or special form of artificial systems. And we will see some examples how learning is done, and especially the math behind this learning. In the third part, we will talk about another form of artificial intelligence. And after that, we will see some math challenges or open questions in AI, which are to be addressed in the near future. And we will finish by a discussion. So, what is AI? AI, first of all, the term AI was invented by the British mathematician Alan Turing. This is the first scientist who proposed the name artificial intelligence. And this is simply to say that the origin of artificial intelligence is math. Math is the science from which have emerged this discipline. And this is some history or basic history of AI. And it began in 1950 by what we call the Turing test in the name of Alan Turing. And I will try to explain in a simple way this test. Imagine that you have a human being asking questions, and these questions may be either answered by a machine or an algorithm, what we call, or computer, and the same question could be also answered by human. And we can say that the algorithm or the machine succeeded the Turing test if the human being is no longer able to distinguish between the answer given by the human and that being given by the computer. And this is, let me say, simply to say that the computer is so intelligent that it is able to respond or to give answer as humans. And obviously, at this stage in the beginning, this was a very, very hard or difficult test for machines due to several reasons, as we will see. The first also marking date was around 1957 with the proposal of the first learning algorithm by Rosenblatt called the perceptor. And in 1986, we have proposed another learning algorithm, which is called backpropagation algorithm for multi-layer neural networks. And another keystone date was in 1969 with Deep Blue. Deep Blue is, let me say, a kind of machine or program specialized in chess playing. And in 1996, it has beaten the world champion at this time, Kasparov. And this really was a marking date in the history of artificial intelligence. In 2016, recently, also, AI has beaten the AlphaGo world champion, which is a very, very difficult game. And in 2018, there is the emergence of OpenAI, which is obviously the company responsible for what we know as ChatGPT. And this obviously has marked a new area in artificial intelligence. But the history of AI is also full of drawbacks, let me say, or fallbacks. The first winter of AI was between 70 and 80, 1970 and 1980. Why? Because in the beginning, we were expecting so much from this field. We were expecting to build algorithms or machines that are capable to solve very hard problems.
What do you
But
represent
due to
in
the
your
lack
curve?
of theory, yes.
The curve represent which indicator?
The history of AI.
No, I understand, but the curve, the y axis represent what?
The curve, yes, I will explain. Yes, this is the interest in AI, the interest in terms of, let me say, research papers and so on.
Okay, thank you.
So we can see a first decrease between 70 and 80. And this is due, as I said before, to as we were expecting so much from this field, and the results were so far away from the results. And that's why there is much less interest in the research community and even in the whole world, even at the application level in AI. But there is another rise in AI in around 1980 with the emergence of what we call expert systems. Expert systems are systems that are able to reason using first-order logical systems. And there is a new wave, let me say, of AI, which has emerged. But these systems, due to their nature, since they are based on logic, they are not able to solve all kinds of problems. And this has resulted in another decrease in interest in AI. But after 2000 and around 2008 especially, there is a new wave, a new interest in AI due to the invention, especially what we call actually deep learning and the emergence of big data. And we are actually witnessing this wave and this interest in AI. And that's why, let me say, almost the whole world now is let me say, interested in seeing what is AI, how it is doing, and how we can profit from this. But in parallel to this, from 2010, there are other hidden factors. which are not visible, let me say, which has also contributed enormously to the emergence of AI, which are first of all, the big storage capacity, since actually with the data centers, let me say, we are able to, with the cloud, we are able to store infinite volumes of data. And this is, we will see, very, very important for AI. Since AI also is based on big volumes of data, which are actually being available also to the emergence of social networks like Twitter, Facebook, Google, and so on, and so on, and so on. So this gave us an enormous amount of data, which is used by AI, and in parallel, obviously, the advancement in GPU, the graphical processing units, which gave us much more computational speed. And these three factors has contributed also enormously in the acceleration, in the interest, let me say, of AI. And just as simply to say that AI has not witnessed only successes, it has witnessed also, let me say, bottlenecks or failures during its history. And now we move to the question, what is AI? So what is artificial intelligence? And before even asking what is artificial intelligence, let's ask what is human intelligence. And I presume that there is no global consensus about what is human intelligence. And this fact is the same for artificial intelligence. There is no global consensus, even nowadays. So what is artificial intelligence? But there is, let me say, some adopted definition, a global definition given by Marvin Minsky in 1968 at MIT. And Marvin Minsky is one of the pioneers, let me say, in the field of robotics and artificial intelligence. And he defines artificial intelligence as the science of making machines do things that would require intelligence if done by men, which simply means that AI is the fact of giving some ability to machines, okay, so that these machines can do things or act or, let me say, think, let me say, like humans. And actually, we are witnessing nowadays 3 stages of AI, and I will explain each on detail. There is what we call narrow AI, or narrow artificial intelligence, in which we have systems which are very specialized, which just means we have computer programs that do special things, but very, very, very accurately. Like, for example, face recognition, speech recognition, price prediction, or whatever. And these systems are specialized. That's why we call them narrow AI. Nowadays, let me say around 2015, we have witnessed another form of AI, which we call broad AI or broad artificial intelligence. And in these systems, we have, let me say, many forms of intelligence, but they are they are working for the same goal, to solve, let me say, the same big problem. An illustrative example is self-driving cars. In self-driving cars, we have so many intelligent parts, but these parts are working together towards a common goal, which is to drive the car safely. And this is what we call broad AI, which we are witnessing actually in our area. But there is another coming predicted area, which is predicted around 2050, what we call general AI, or general super intelligence. And in this area, we will have some form of AI which will be able to do so many tasks, not special, for example, solving problems in math, so in medicine or whatever, and without being specialized. And this form of AI will have some kind of creativity. And it is even expected that it will go beyond the human intelligence, which means that we may have some programs or some machines or some robots which will be more intelligent than humans and are able to work in any field, any time, without being specialized in any field. And we will see why this fact is coming anyway, and what are the factors that are contributing actually to the emergence of this general AI or super intelligence AI. So this is just an explanation of these fields. We must ourselves some questions. So how this AI works? And simply for us as computer scientists, AI is nothing more than machine learning or machine algorithms. So AI is about algorithms. But what is special is that these algorithms do not work like classical algorithms. They work by consuming, let me say, data. So these algorithms are data intensive, which means that they're based on data. And this is special to machine learning.
Sorry, I think that Professor Ben Romdhane has a problem with the net, and he will be online as soon as possible. Sorry.
رفيق ده مشكلة.
Yes, I think that Professor Ben Romdhane has a problem.
He's disconnected. Do you think that he's disconnected?
Yes. He's
Okay.
not here. Just 1 minute, 2 minutes.
Okay, we will wait.
We are sorry.
Sorry, really, again. So after these main concepts about AI, let me say there are questions we should ask ourselves. So how AI works? Simply, AI works using machine learning algorithms. So for us as computer scientists, they are nothing more than algorithms. Let me say, like we said, there is no magic behind the scenes. So they are simply algorithms executed by machines. But what is particular for these algorithms that they are based on data. They are data consumers, even intensive data consumers. So this is a kind of algorithm, as we will see it, which works on data. And data is a major component in AI. We cannot do AI without data. And there is no AI without data nowadays. The third major question is how efficient are they? So for this, we use some metrics, we call it metrics, or let me say mathematical formulas to score them, to give them, let me say, a score or credit for achieving some tasks. But what we should say also is that nowadays there are no perfect, let me say, machine learning algorithms. There is no algorithm which is 100% perfect. So which means simply that they are doing errors. And we will see to the importance of this fact or of this error. But we should also remember that even as human beings, we are also doing errors. So even us as human, we are not perfect. There is no perfection in our thinking, our reasoning, or whatever. We will begin now we'll move to the second part of this fundamental concept, to deep learning. And I will begin by a first field or first example, which we call bionics. So what is bionics? Bionic is simply building artificial or mechanical body parts that attach to the body. And we will try to make them function as normal or biological body parts. And these, let me say, artificial mechanic body parts will be seen as a natural extension to the body. And these, all of us has witnessed these movies, which at this period were pure science fiction, okay, in which we are seeing robots moving and doing so many tasks like human beings. But nowadays, this is no longer science fiction. And in this, let me say, image, we are witnessing an AI-powered leg at the University of Michigan, which is an artificial leg, which is directly connected to the brain. and is powered by AI, and it is functioning like, let me say, a biological brain. And this is another example of Professor Huger, which I have met him personally. Donc, Professor Huger is the MIT Bionics group, Bionics research group at MIT, which he's heading. And we can see that he has 2 artificial legs. And with these artificial legs, he is doing, let me say, almost impossible or very difficult tasks like climbing mountains. And which is a very, very hard task, even for human, let me say, normal humans with, let me say, biological legs. And this is to show that these legs, that these artificial legs has reached nowadays a very, very high efficiency and a very high, let me say, accuracy. And they're acting like, or somewhat like, biological, let me say, legs, or this is true also for other parts of the body. And the major question we are asking ourselves, we should ask ourselves, how this is working, how these AI-powered, let me say, mechanical parts are attached to the body, and how will they work. So this is an example of an artificial limb. But what is true for the artificial limb is true for any artificial, let me say, part of the body. So we have as a major component our brain. And second component, what we call interface chips, okay? And these interface chips, their role is to intercept or to receive signals from the brain, signals in the form of EEG, or electroencephalography signals. And these signals will be transformed some way to movements by some artificial system, by some AI, and which these movements will be transmitted to the artificial limb. Okay, so summarizing, we have 3 major parts, let me say, or 4 major parts: the brain, the interface, which receives signals to the brain and which transmit these signals to the AI system, and the AI system which will transform these signals to the artificial limb. And in this way, the artificial limb will move like a biological limb, receiving directly signals from the brain without other components. And in this case, we are using a special form, let me say, of artificial intelligence, what we call recurrent neural networks, which is a kind of deep learning. And obviously, this system is learning on data, and we will see what kind of data it will learn on. But this system, once we have made learn the system, it will be embedded on a chip and attach it to the body and link it to the neural interface, and to the limb or to the artificial body, and this is the whole game. Okay, and the artificial limb will act as a let me say, biological part of the body. Another example is self-driving cars, and this is, for example, a driverless taxi in San Francisco in California, which is already operating. The taxi, which is operating on its own, it is receiving calls, it is taking drivers, it is putting them where they want to go, it is recognizing speech, since clients can speak, let me say, with the driver, with the autonomous driver of the car, and so on, and so on, and so on. And this is a kind of, let me say, what we have called broad AI. We have so many AI systems which are coupled together to one unique goal, which is to have a self-driving car. And this self-driving car, like we see it in this figure, it is composed of many AI parts. One for perception and localization, one for path planning, one for behavior arbitration for drive, and one for motion control of the car, and so on. And these cooperate together to drive safely on the road. So far, what we have seen, 2 examples of the use of artificial intelligence. The first is about bionic limbs, and we have used a special kind of deep learning, which is called recurrent neural networks, and we will see what is it. And in the second example, a self-driving car, and it is using another form of deep learning, what we call convolutional neural networks. And this is simply to say that artificial intelligence is nowadays applied, let me say, at large scale, and even in some, let me say, sensitive situations, which is our body, our lives nowadays in everyday life. So now we will move to another part, which is deep learning. So in these two examples, I have talked about deep learning. So what is deep learning? The major question, what is deep learning, which is a kind of, let me say, of AI. Deep learning is a type of machine learning. So there is a general field we call machine learning, and deep learning is a subfield of it. And it is based on artificial neural networks. Obviously, what are artificial neural networks? Okay, and you will see what are artificial neural networks. And the term deep refers to the fact of using a cascade, let me say, of neuron of layers. And each layer will have an abstraction, let me say, represent an abstraction level of data. As we see it in this example, we have so many parts of the image, okay, of the elephant. We have the points, we have the segments, then we have the whole form of the elephant. And this is a kind of deep neural architecture to represent an elephant or whatever animal it has. And deep learning has gained interest since 2010, like I said, due to several technological factors. The first is the fast processing speed, since to do machine learning or especially deep learning, we require much computational power, and we require also high volumes of data. Okay, and actually we can afford these two, let me say, criteria. So I will begin by the basics and see what is an artificial neural network. So what is a neuron? In this slide, we have a biological neuron, and we have an abstraction of it, which is the artificial neuron. So the artificial neuron is nothing more than a mathematical representation of the biological neuron. So what do we have? We do have actually, essentially, the following parts. We have input signals, okay, which will be transmitted to the neuron through some connections. So the neuron will receive, we will see from where he will receive it. Will receive some signals, okay, through connections. Then we will sum these connections and pass it through a gate or an activation function, which will produce an output of the neuron. So the neuron will receive many inputs and will produce one output, one signal output. And this output will go somewhere. And from a mathematical perspective, we have so many activation functions. We can have any activation function like the sigmoid, rectified linear unit, and so many others. And this is simply to say that, like the biological neuron, we will receive signals, and these signals will be combined together, and the output will fire. The neuron will fire or output a signal. And an artificial neural network is nothing more than a set of neurons, of these computing units, of these elementary computing units, connected together and organized into layers. So in artificial neural network, we generally have many layers, okay? We have the input layer, which will receive the input data. This data could be either be it numerical, textual, whatever kind of data. And we have hidden layers. And we have the output layer, which will output the signal, let me say, of the network. And in between, we have the hidden layers, and all these layers are connected together through connections, which we note why in this slide. So from, let me say, a mathematical point of view, we have an input data D, we have a set of connection Y, and we have an output signal, which depends on both the weights and the data. And this is what we call the function realized by the neural network. So a neural network will do some computation given this neural architecture. And there is, let me say, a major theoretical result, which has really boosted the research in neural network. It was in 1989. And this result, what we call the approximation theorem, okay, or approximation capability of artificial neural networks. This theorem simply states that a neural network with hidden layers can approximate any mathematical function to an arbitrary decision. And this is very, very important, since this shows us that from at least a theoretical point of view, an artificial neural network can compute any function to, let me say, an arbitrary decision, or proceed, all depending on the number of layers given the size of the layers, that is the number of neurons in each layer, and so on and so on. And obviously the proof is given in this paper, which is called multi-layer feed-forward networks are universal approximators in the journal Neural Networks. Now, when we talk about artificial neural networks, there are two concepts that we should fix. The first concept is the architecture, and the second concept is the learning algorithms. So what is the architecture? The architecture is nothing more than the number of layers in the network, given the hidden layers also, the number of neurons in each network, how these layers are connected together, and so on and so on. And this gives us the architecture of the neural network. And as we can see in this figure, there are many possible architecture for any neural network. Okay, you can do design in what kind of architecture you want, obviously for a given purpose. And the second point is the learning algorithms. Once you have this neural network and you have connections between neurons, these connections must be learned. And for this connection to be built or to be learned, we have to use some kind of learning algorithms. And obviously, this learning algorithm will give us how these connections are computed or are updated. So when we talk about artificial neural networks and we talk about deep learning, we have to fix these two, let me say, concepts, or these two parameters, the architecture and the learning algorithms. And we will begin by our first recurrent neural network. We are going now deeper, let me say, in the technical details. A recurrent neural network is composed of 3 layers, as you see it here, okay? You have one layer, which is the inputs, hidden layer. We may have one hidden layer, we may have 2 hidden layers, 3, depending on the architecture. And obviously you have the output layer. But what is special about this kind of neural network is that the input to the hidden neurons or the hidden layer is coming from the input data and also from the output of the hidden layer at the previous timestamp. And this kind of neural network is, let me say, is dedicated to learning what we call sequential data or sequence data. For example, of sequence data, a phrase. A phrase is nothing more than a sequence of words, and a word is nothing more than a sequence of characters. So the order, the correlation, there is some correlation between the input data in time, okay? Like time series data, like DNA data, and so on. And the input at timestamp t for hidden neurons is becoming from input data from timestamp t, let me say, and from the hidden layers at timestamp t-1. And this is obviously the objective is to detect what kind of correlation there is between data through time, okay? And this is explained in this slide. As we will see, a hidden neuron has inputs from input neurons at timestamp t, and from the output hidden layer at timestamp t-1. And obviously the activation, what we call, of the signal of this neuron is nothing more than the summation of these two quantities. Okay, and obviously this activation goes through an activation function, which is called theta in this slide. And this is obviously give us an idea about how these this recurrent neural networks learn, and this gives us an idea why we call them recurrent. Recurrent because they take their time, they take their input through time at timestamp t, and from the output at timestamp t minus 1. And obviously, for the output unit, we will compute its activation from the previous hidden layer. Okay? And the previous hidden layer is computed from the previous, and so on and so on. And this gives us a cascade, let me say, of propagation. But when we reach the output layer, we'll be able to define what we call a loss function or an objective function. Like I have, and in this, like you see it in the slide, we have a computed output by the neuron or by the neural network, and they have a targeted output, a desired output. Okay, what we call the class of the data. This is kind of let me say, supervised learning. And the difference between them gives me an idea about the error done by the system. I give a simple example. For example, I want to make or to develop an artificial neural network for image recognition, for face recognition. So what I will introduce is the pixels, let me say, in the input of the image, and I will put the same image at the output. And the computed image by the network will be compared to the target image. And if there is a difference, it will give me a certain quantity, a certain loss function, and this loss function will be the error done by the system. And obviously, what we want from learning is that the system makes the least error. So we have to optimize this function, and that's why I have insisted on the output layer. It is in this output that we define the objective function that we want to optimize. And we will optimize this function using gradient descent or ascent techniques, as you already know them. And we have to compute these gradients and so on. With this, give me the following possibilities. So gradient descent, I input data in the input layer, and then I receive a signal in the output layer. I will compare them in each data and compute the gradient on each data. I can also, to make learning much less computationally expensive, I can do on batch of data and a set of data, not single data by data, but I compute the average gradient on set of data, which this gives us what we call the stochastic gradient descent. But in both cases, I'm trying to optimize or to reach the global minima of a function using gradient descent techniques. And this is how is done machine learning. And the adaptation of these weights will produce less error in the first iteration, next iteration, and so on. And with this gives us what we call one of the most famous algorithms, backpropagation through time. And what is backpropagation through time? We have two phases, the forward phase and the backward phase. On the forward phase, we'll propagate a signal from input to hidden, inputs layer to hidden layer, from hidden layer to hidden layer, and so on and so on. And finally, from hidden layer to output. At the output, we can compute some error. So what we will do, we'll compute the gradient of this error at the output and retro-propagate it. This gives us the backward phase from output to hidden, from hidden to hidden, and so on, until from hidden to input. And in this way, we update the weights. This is what we call an iteration of the machine learning. Once this iteration is done, even starting from random connections, the error will be minimized. And in the second iteration, it will be much more minimized, and so on until we reach a global optima through iteration. And this is how really machine learning is done in this kind of artificial neural networks. And as you see it, as I said before, there is no magic behind the scenes. For us, these are simply algorithms which have some mathematical foundations and which are operating on data. And more you have data, more your trained model or your artificial neural networks becomes more efficient. Now, I will move to another form of artificial intelligence, which is a little bit different from the first, but it will use the same concepts, which I call generative artificial intelligence or generative AI. Okay, and I will begin by these two examples, by these two cats. Okay, please observe well these two cats and tell me if there's something special. Please, if there is something special, write it on the chat. Now we'll move to these images of humans. Okay, and what is really common between these two cats and these, let me say, humans, is that none of them is real. No one of these human or these cats does exist in reality. And they were all generated by AI, generated by artificial general intelligence, and we will see what kind of models is used to generate them. Much more or less about me. So as you see, this is a picture of me generated by AI. And as you see in reality, I am far from having long hair and so on. Okay. So now we'll move to this kind of generative AI. It uses a special kind of neural networks we call GANs. GANs for generative adversarial networks. Okay, and I will explain each term separately. So we have especially principally two artificial neural networks, deep neural networks, which can be recurrent neural networks, convolutional neural networks, depending on the application and the data you are using. We have what we call the generator and the discriminator. And the generator, what he will try to do is to generate fake samples, but it will generate fake samples based on some latent space and some, we'll see, probability distribution. And we have some real data, okay? And the discriminator, which is another neural network, will try to disseminate or to distinguish real data from fake data. If he is able to discriminate, then that's okay for the discriminator, for this neural network, but this is not okay for the generator, since the generator has produced a sample which was easily detected by the discriminator. And we will see what we will do. If, on the opposite, the discriminator was not able to distinguish between real data and fake data, then obviously we can see that the generator has succeeded, somewhat succeeded in fooling, let me say, the discriminator. Okay, and this is, as you can see, like they are working in adversity, one against each other. The generator G is working against the discriminator, and so on and so on. Okay, and I will begin by giving details of the generator. So we have a generator G which generates fake data. So he will take a sample data X and add some noise to it using some probability distribution. So he will try to distort the data. In this slide, you can see that I have a picture of the Mona Lisa and we have added some noise to it. So this Mona Lisa is no longer real data. It is fake data. It is distorted. I have added some noise. Okay. We can also use other forms. We can let the generator generate data from scratch, but using some probability distribution. Okay, like any kind of distribution we want. And the discriminator will take as input a couple, real data and fake data. And he will try to distinguish them. Okay, he will try to compare them and say, classify them as fake or real. Okay, and once the discriminator classify the fake data as fake, then he has won. Once the discriminator classifies real data as real, fake data as real, then he has lost. the game, like we say, okay? And we will see how this is done in reality, and how machine learning is done on this case. And the discriminator is trained to maximize the following expectation function. Okay, log of ddx. ddx is the output of the discriminator, which is either 1 or 0, let me say, in numerical values. And as we can see it from this definition, this error is maximal when real data is classified as real. Okay, when ddx equals 1. Okay, but the generator is trained to minimize the opposite. From the expectation of a log 1 minus d digit z, and we can see that what is this d digit z is the classification of the discriminator of the data generated by the generator. And we can see that this error is minimized when the discriminator classifies the fake data as real, which is simply means that the discriminator is fooled by the generator. And in this case, well, you can see that the generator has won. So we will try to make learning, or to make learn this system using this maximize, minimize process, and we will see what happens. So the discriminator and the generator will play what we call a minimax game by trying to, let me say, optimize this function in the general sense. And we will alternate learning between G and D, or the generator and discriminator, by using gradient ascent of the discriminator, since we are maximizing, and gradient descent on the generator of the same function, since we are minimizing. And obviously, at some point, neither the generator will be able to further, let me say, foolish the discriminator, neither the discriminator is no longer able to distinguish further between what is fake and what is real. And this is what we call in game theory the Nash equilibrium. And when the Nash equilibrium is reached, we stop the learning process, since none of these two players, okay, will win if he changes his weights or changes his strategy. Okay, and this is in game theory we call the Nash equilibrium. And I will give a simple illustrative example of this. So this is the algorithm. When we learn the systems, we have the first part is how to make learn the discriminator, okay, by a gradient descent technique, as we have seen before. The second part is for the generator, and this obviously will repeat this min-max game of this process until no further improvements in learning, or further improvements in weights, or no further changes in weights or on the performance either of the discriminator or generator. In this case, we say that we have reached the Nash equilibrium and we stop learning. And this is excuse me, a simple example, a 2D simple example. The blue line is the discriminator, the green line is the generator, and the black line is the real data. So real data is real, it does not change. As you see it in the first iteration, the generated data by the generator, the distribution is far from the real data, okay? But as long as we move the process, the learning process, the same process through one iteration, two iteration, three iteration, we see through iterations that the distribution of the fake data is approximately the same as the real data. This simply means that the generator, which is generating fake data, produces almost real data. And this is the Nash equilibrium of the discriminator. This means that discriminator will no longer be able to improve his results. At this stage, we stop learning. Obviously, this min-max game of this discriminator architecture will apply to generate any kind of data, all depending on the neural architecture used in G and D. You can use it for images. You can use it, in this case, we use CNN or convolutional neural networks. You can use it for, let me say, text. In this case, we have sequences. In this case, we use RNN or recurrent neural networks, and so on, for videos or whatever. And this is how fake data is generated, and this is what we call generative AI. Generative AI, like ChatGPT, is nothing more an AI, deep learning model, which is generating, in this case of ChatGPT, generating text or documents or whatever, or videos or whatever kind of data you want. So far, now we move to, let me say, an important part, which is AI and math challenges. Because there is, I have witnessed it me myself as a computer scientist, there is some gap in research between the both disciplines. Sometimes mathematicians do not know that AI is basically maths, and computer scientists, especially when they are working in the application field, this means they are using AI just for application, do not know that AI is basically maths. Okay? And making the link between two is a very, very important task, and will boost, let me say, further this field, and make it more challenging. And you will see here some, let me say, open problems, or still open problems in AI. I will begin by the most technical one, which is non-convex optimization, which is the first challenge. When we make machine learning, be deep learning or whatever other of artificial neural networks learning, we are defining loss functions or objective functions. And we are optimizing these functions using gradient descent or gradient ascent, depending on either we minimize or maximize techniques. So this kind of, let me say, optimization may lead to convergence to local optima. So we may not be able, through the learning process, to reach what we call the global optima of on the landscape of these functions. This is the first thing. The second thing, we may have very low, slow convergence rates, which means that before stabilizing the neural network or the neural system may take a very, very, very long time. And this is why we need so much processing, okay, power, especially when we have large amounts of data. And one difficulty is long-term dependency, especially for ADN sequences of the Arab language. We have very long phrases in the Arab language, which make very, very long dependencies. So which gives us much more, very, let me say, big architecture in the term of neurons and in the term of hidden layers. And this is very, very challenging at the practical level to use this kind of technology or this kind of learning for this field. And this raises another problem, which is what you call the vanishing and exploding gradient. And from a mathematical perspective, computing the output at iteration t is time, depends on the matrix of the eigenvalues, okay, to the power of t, okay? And this matrix of eigenvalues, if it embeds numbers much less than 1, then it will vanish. If it embeds numbers much bigger than 1, that it will explode. Okay, this simply means, in terms of learning, either the system would stabilize and we will have very, very slow convergence rate on the surface, or on the surface of the landscape of the gradient, or either we will jump very quickly, and this gives us a non-stable algorithm. Okay, and really it is very challenging to find an optimal theoretical solution to this problem. Obviously, there are, let me say, approximate solutions, which what we call, we use time, previous steps to, let me say, to compute the current gradient and so on, but this are just heuristics and nothing more. This is not really an optimal solution for the problem. Another challenge is mathematical reasoning. Okay, actually, as you witness it, the use of AI or machine learning has not confronted the field of reasoning. And one challenge is how to use these machine learning or AI in mathematical reasoning. Why mathematical reasoning is difficult? Because it involves many steps, and like theorem proving, like geometry problem solving, and so on and so on. We can illustrate too many problems of this kind. And there are link between steps, and we have to find some way of algorithm, we say, reasoning algorithm that goes from one step to another. Okay, and these logical, steps, it are actually very, very difficult to build or to infer or to compute for an AI system. And an interesting approach would be to build mathematical models that are able to reason, okay, to prove theorems and so on. And this may be very helpful in, for example, learning or whatever. Another, maybe much more challenging, is discovering new mathematical concepts. Okay, and AI, machine learning, can assist us in identifying novel concepts which we don't know. Actually, we have a set of tools. We have a set of mathematical tools, basic tools, which we are using every day, the theorem of X, the conjecture of Y, and so on. But one major question here, combining or maybe putting all these concepts together in a machine learning system or an AI, will it be able to produce other novel concepts that to up to date or to nowadays humans we were unable to produce? And this is a very, very challenging question. Now, another challenge is what we call trustworthiness. And this is very important concept. Why? Because AI is basically used for decision making, like in self-driving cars, okay, chirurgical robots, and so on and so on. So
Us again problem.
We lose it again.
Yes, yes. We have to wait him just 1 minute.
our lives may depend on them. And one way is what we call explainability, what we call explainable AI. And actually, we're developing models that are able to explain their decision. And in this way, they will give more trust in AI. But the actual explainable, what we call explainable AI, has reached only a small part of machine learning algorithms. And especially in deep learning, there is no mathematical model for explainability. So it will be very challenging to develop mathematical models that are able to explain the decisions made by deep learning systems. Another challenge is generalization. So machine learning is based on data, okay? But generalization capability is tested on unseen data. Example, I train my system on human faces, but I will test it on unseen faces. So one theoretical issue, could we predict generalized limit or boundaries of these models since the learning phase? Given in learning systems, I am able to predict what are the boundaries of its generalization capability. And actually, there is no way, no mathematical models that can do that. Voilà. Now, I will finish by a discussion. So we have artificial intelligence, which embeds a special field called machine learning, and which is special and very specific field, which is witnessing a very, very high, let me say, which is increasing rapidly, what we call deep learning. But at the heart of all these models, there is math. They're based on mathematics. They're based on mathematical theory. And the open question of challenges are optimization methods used in these learning algorithms, mathematical reasoning, new mathematical discovery, explainability, and generalization. So what's next? And this is an important question. All of us is witnessing the emergence of quantum computers, okay? And in this case, when they will become, let me say, available to the public, these quantum computers will be able to learn on very, let me say, very rapidly. So algorithms will be much, much faster, even using infinite amounts of data. Okay? And obviously, these quantum computers, coupled with mathematical theory, will give a new era, which we are expecting around 2050, which is what we call the human, let me say, the artificial super intelligence, in which maybe machines may go beyond the, let me say, the average human intelligence. And thank you very much.
Thank you. Thank you.
A lot of thanks to the Professor Lotfi Ben Romdhane for this nice talk. Please alert some questions.
Yes, please.
Okay,
Yes.
hello, Lotfi. Could you please go to slide number 14, 42, 42.
42, okay. Yes.
Yes. What do you mean by the symbol E?
This is the expectation.
And the index, X tilde P of Z, Z.
Z is
little bit obscure for me.
Is the North distribution. Since this is the generator will use some noise on the original data to produce fake data.
No, but there is an index in the expectation. You mean what do you mean by the index Z tilde P Z Z?
This is the expectation. It simply means the expectation over the distribution Z.
And PZZ has a meaning also, no?
Yes, this is the probability of the probability, yes, of Z. Probability
And
distribution.
And this distribution is fixed by the user or the user
Yes.
or okay.
Yes. Yes, you can use any kind of distribution. Here, honestly, there are many varieties. You can fix a distribution, okay, and generate, distort, let me say, the data according to this distribution. Or you can make a learning system, okay, which will learn a certain distribution and will distort according to this distribution. But the idea is that what you will do is to make, how to say, to take the real data and to distort it, to add some noise, let me say, to some extent. And it is very clear to see it in this image. Like, for example, I have this image, okay? What I will do is I will add some noise to the pixels. So like the image will change. For example, in the second image, you have like a smiling Mona Lisa, which is not really. And you have like not smiling in the first one. So I have to distort the data to get fake data. But this, let me say, this fake data, I will add some noise to the original data. Okay.
We have a question in the chat from Professor Mohammed Mudassir Hassan. His question is, can we use AI in chemical graph theory? Will it give accepted results instead of using ordinary computations techniques?
Yes, chemical.
Yes, chemical graph.
Yes, chemical graph. Yes, yes, of course. Yes, and it is. We have begun using it. There is another kind of neural networks, which is what we call graph neural networks. And these graph neural networks do what we call graph embeddings. Like they are able to learn not only data, but data like graph structures, like chemicals, okay? And we are using even this in social networks. Actually, I'm using this in social networks since the social graph, like we call it, you have some individuals are connected together. And what you will learn is the whole graph. We do some graph, let me say, embedding. And this is also true for chemicals. Yes, it is already, we can use it without problem. And it is very, very efficient.
Is the Nash equilibrium almost surely reached in general?
Nash equilibrium, excuse me?
Is the Nash equilibrium reached almost surely?
No, I will come to the slide. This is a very, very important question. Okay.
Yes.
Yes, this is it. Yes. There is no real guarantee to reach this equilibrium. And this is true for this kind of GANs learning or any artificial neural network. Even if you use, let me say, an ordinary artificial neural network, you have no real guarantee that you reach, let me say, the optimal solution. Okay? And there is no guarantee that you reach this equilibrium. So like your system will oscillate, will
Okay.
every player will change his let me say his game, and you reach no equilibrium. But what we do in practice is that we fix a maximal number of learning phases. Going beyond this number, we stop learning. Okay. And to see what is not going for to make the system reach. This is kind of, let me say, engineering.
Okay. And the number of steps, it depends on the choose of a generator G, or the number of steps to reach this equilibrium.
It depends on both the discriminator and the generator.
Okay.
Because what you are in one step, this is the algorithm, you are making the learning of the generator and the learning of the discriminator. It is like alternating between the two players. Okay. Like you get some data, you propagate it in the network, you make the discriminator learn, then you make the generator, given the result, you make the generator learn, and to see the result. If the discriminator has won, then the generator has lost. And in this case, you will penalize, let me say, the generator and ask him to produce much more realistic data. And so on and so on. And the equilibrium, what we call the equilibrium, that it is a state in which we cannot further improve the discriminator, and we cannot further improve the generator. So at this stage, we stop learning, and we say that that's okay. There is no further steps that could improve the system.
I have a general question. You think that the AI will be able to resolve some complicated scientific problem in math, for example, or in physics or something else? In the future, will AI be able to resolve some conjecture, for example, in mathematics, for example? For example, 2050, as you were.
Honestly, as a specialist in the field of AI, I will say maybe. Honestly, I'm not sure 100%, but maybe, because actually we are witnessing so many things done by AI that we were not expecting before. Personally, I have been working in AI since my PhD thesis. I have worked on artificial neural networks a long time ago. I was not expecting that they will become so efficient nowadays, like these days. Even myself, I was not expecting this. But will they be able to solve scientific problems concerning, like this is what I have pointed, like one of the challenges to make new discoveries? Maybe yes, maybe not. We are not honestly at this level of, let me say, of human intelligence. But even for humans, not all humans are making discoveries. So very few humans are making discoveries. So what I'm quite confident about is that AI actually can assist us in many tasks which were, let me say, difficult to some extent before. Okay. And as you can see, for example, in ChatGPT, you can use an assist to write whatever you like without really big problem. Okay, so it is really at a very, let me say, good, satisfactory level of performance. This does not mean that it is perfect. But what I'm trying to say is that what is coming in the future, in the near future, we are living an exponential curve, what we call an exponential curve, and things are accelerating rapidly. Maybe 2050 we will witness a new theory or a new maybe learning algorithm, because actually there are some new let me say machine learning algorithm in another field, which is what we call quantum machine learning. And things using these algorithms, maybe things will change much faster. Maybe we'll be able to make learning much more rapidly. We can make learning on all existing data using quantum computers, and maybe in this case we will be able to solve, let me say, some difficult problems like any conjecture. Like, for example, doubtless you know, or you already know about the P versus NP problem, which is in computational complexity.
Yes. Thank you. Are there other questions, please?
Assalamu alaikum.
Salam.
Wa alaikum salam. Hello.
Thank you very much for your interesting talk. Can we go to slide number 42? I have a small question there.
Yes, please.
Is here in the first, you said that the discriminator T is trained to maximize this expectation.
Yes.
And you said that the error is maximal when the real data is classified as a real.
Yes.
Now, when the real data is classified as a real, it means the error should be the minimum, or I'm getting it wrong.
The error, when this error is maximal.
When the error is maximum, which
Yes.
my understanding is if the real data is considered as or classified as a fake, so we have a very large or maximum error. But if the real data is classified as a real, it means there is no error or a very minimal error. So why we are maximizing the error here? We are saying the error is maximal at this point.
No, you're talking about the first line, excuse me? The discriminator.
Yes, this one exactly. The first,
yes.
The third line actually.
Yes, because DDX is probability output. DDX, the decision. Normally, when using the logistic function, is a number between 0 and 1. Okay, let me say mathematical. So it is when DDX equals 1, which is a correct classification, then the error is maximal. Otherwise, it will be negative. Okay. So we try to maximize this error, but on the opposite, the generator will do the opposite. Okay. Right. Why he will do the opposite? Trying to fool, let me say, to make the discriminator make an error. Okay, make an error like taking, let me say, the fake data as real one. Okay, and if the generator has won the game, let me say, this means this error is minimized. The second error. Okay, that's why we use both the sum, the global, let me say, min-max game, what we call min-max learning, is the sum of both errors. Okay, and you can see it in these examples. Okay, so you see that these images are fake. This image, excuse me, excuse me, I don't know. You are seeing you are seeing this image?
Yes, yes.
Who is this?
I don't know.
Lotfi Ben Romdhane. No, yes, it is Lotfi Ben Romdhane, but really it's not Lotfi Ben Romdhane. This was an image generated by AI, and so it is really very real image. Okay, so but this is what I wanted is to give you an illustrative example. What this is an image generated by a generator taking real images, so and adding some noise, but the discriminator will try to distinguish what is fake from what is real, and when learning is stopped, the noisy data is really real, and you can see this is as if it was an image of me. This image has never existed. I have never long hair. I have never.
Yes, but you could have long hair. It's possible. It's not.
It's possible, yes.
In the future.
No, this is I'm giving this example because maybe in 1 minute I open the debate, because in the social media we are facing what we call fake news or fake data. Okay, like images, I can show you, even if you want some videos, text, and so on. And in the social media now we can post data which is generated by AI, even soft bots, like let me say fake accounts, and nobody will be able to distinguish or saying that it is fake data. I can put this picture on my profile and it will be taken as a real picture, not a fake picture. This is the real danger. This is what I call the social war.
Can I ask a question?
Yes, please.
For the minimization process, when
Yes.
you use, I
The
don't know,
gradient descent.
yes, for any algorithm. Here you say that we know that the function that we have to minimize is not convex. Then we can have several local minimums.
Yes.
What is the guarantee that the local minimum that we are going to reach is a good minimum? Is there a guarantee for that or not?
In theory, no. We
Okay.
have no.
And then what? And how in practice it works?
Yes, I will tell you how it
Why?
works. Yes, in practice it works because in theory, no. And this is one of the open questions. Could we have some, let me say, mathematical models which will be able to evaluate this learning process and what is the quality, let me say. But what we do in practice is the following. Once learning stabilizes, like we have reached a minimum, okay, what we do is we take another set of data, which we call test data, okay, and we test it on the learned systems. If he, like, let me say, asking questions to the neural network, unseen questions, okay? And if the answers are satisfactory, then we can say, okay, learning is good. We can stop it at this phase. And we have
Then you
two
mean
kinds
that
of data. We have learning data and we have test data to test the learning quality of the system, okay?
okay, but then what you mean is that if it not a good answer, we repeat the process with
Yes, we will repeat the
again
process.
and again and again until reaching a good minimum.
Yes, again and again, because in learning algorithms there are so many parameters, what we call free parameters, okay? And we can change the learning rate, we can change whatever the starting point on the surface, because initially weights of the connections are on general initialized in a random manner and so on. There are so many ways to restart the learning process. We can shuffle the data. We can to present it in a random order and so on and so on. For example, I give you an example. In ChatGPT, and it's, I think, 4th version or 3.5 version. I don't remember exactly, but I have it in all the slides. It has like 10 billion parameters, free parameters. So imagine.
Okay, thank you. Thank you.
We have to thank again Professor Lotfi Ben Romdhane for this nice talk. Before stopping this session, we have to conclude the activities of this webinar for this academic year, 2023-2024. I thank everyone for attending the talks throughout this academic year. We wish you a good holidays and hope to see you during the next academic year, where a part of the program is already ready. And we think that we start the next year in 17 September with Haider from the University of Bourgogne. Thank you again, Professor Lotfi. Thank you for all the public, and bye.
I will take the opportunity
Thank you very much.
of
Yes.
this conference on artificial intelligence to make an